So hi guys, this is the lecture one, part one series of the course. So I'm guessing that you're here to start, and I'd just like us to dive into it and just be open to learning, and it's gonna be fun, regardless of the video being a video. So this is gonna be the pattern for us. We're going to do lecture one, part one, lecture two, part two, down to lecture four, and I'm making it short so that you'll not be bored from it, because if it's too long you get bored. But you can watch it in parts, but we're going to be doing this weekly. So let's just go right into it and start. So this is me, in case you've not seen me or you didn't realize it was. So this is the lecture for chemistry, and we're going to start off with matter and measurements. And in the course of the classes, I would like to be encouraging you to pause and try to answer or think of the question. You're in your house, so you can literally write what you think is what I'm asking, or solve the equation, or solve whatever it is, so that you'll be more interactive. So you can solve it and see whether it matches what you've solved already. So it's more engaging. So this is what I encourage you to do, and I trust that if you do it, you won't regret it. It's not going to be so bad as me not seeing you physically. So let's just get right into it. And the first question is, what is chemistry? Yeah, some people have been doing chemistry from high school, but they've never stopped to think, oh, what is this thing called chemistry? Some people start saying maybe it's atoms, it's electrons, or in fact, I've had people say it is everything. And then I say, well, wonderful, nice answer. It's everything. How can chemistry be everything? What about physics? What about biology? What about mathematics? What about all of those other things that are not everything? So basically, if you have an answer you can give, or write it down. So chemistry is basically a study, and that's what you're here for. You're here to study the study, and that's why you're a student. The word study, student, stud. So it's a study, and it's a study of matter. That's what we're looking at, matter and energy, and how they interact between each other. And it's very interesting that people don't even realize it. In fact, you might have not realized it, that you do chemistry every day, whether knowing or unknowingly. And the products of chemistry are all around us, from the toothpaste you probably will use to brush either this morning, or that you used this morning, or will use this morning. It's product of chemistry. You took a shower, soap, water, all of those things. Good water, because the water can be salty. Chemistry helps to purify the water. And then you have the kitchen, cooking. When you cook your meals, basically you have some chemistry going on with the oil, with the spices. All of those things are all chemistry that plays out in itself. And if you love sports, football, basketball, whatever sport you do love, there's some chemistry that goes on that is very important. If the players don't have good chemistry, they will lose the tournament. In fact, they will lose the match and lose the tournament eventually. And if the athletes don't know what they're eating, what they need to eat, how they need to rest, bad chemistry will always result in failure. So people have lost their lives because they lacked good chemistry. So chemistry is actually good, and something that you need to learn, know, understand, and see how it applies to your now. And let's just get right into it. So I think I've created in your mind's eye that some people hate chemistry, not because they know chemistry, or because they don't know chemistry and they hate it. And sometimes it's because of the teacher they had back in high school that was just like this, or because they are just scared. Too many formulas, too many elements. But chemistry is a friend if you get to know him or her. Is a friend. But you just can't be at the door and you're saying the house is ugly, or you can open the door and walk in and see that the house is beautiful and it's not as bad as you think. So that's my encouragement before we get into it. So just try and get past the doorknob, turn it open, and walk in and try to make yourself feel comfortable, and you will not regret it. You might just change your mind, and I'm hoping to change your mind about it. So for the first lecture, we're going to be looking at matter and its measurement and measurements, because chemistry is a quantitative science, so you have to measure. So, and matter is anything that has mass and occupies space. So matter is basically everything around about us. That is the part of chemistry that is everything. That's why most people tend to say chemistry is everything. So that's it for it. So we just go right into it. Sorry, just go right into it. That was a mistake. I was supposed to go down. I went to another scene. So in this outline, we'll be looking at matter and its classifications. We'll look at measurements and the properties of substances. So after that, let's just go right into it. So as I said earlier, I'm repeating myself now so that you remember what I said by looking at it. So chemistry is basically concerned with matter and energy and their interaction with each other. As the interaction of matter and energy is what chemistry is based off, is a study. It's based off that. And chemistry forms the foundation of other disciplines. So no matter what course you're studying, chemistry is the foundation. And foundation, for you to build a building, you have to first and foremost dig deep, make a foundation, and place the building on top. And the most important part of the building is its foundation. If a building's foundation is horrible, you have a horrible building. And I love the fact that in this place they take a lot of time to do their foundations, because there are earthquakes that can happen, and if you don't have proper foundations, your building will just drop. And there are bodies that ensure that you don't make any mistakes with your foundations, especially if you want your building to go higher. You have to have a good foundation. So if you want to go higher in your field, the foundation of chemistry, which is the first course you take in your first year mostly, has to be good enough. So chemistry is the foundation for engineering, health sciences, pharmacy, and pharmacology, because all of those things need chemistry. And some of you, or most of you, or some of you students are computer engineering, and then you'll be like, what am I going to do with chemistry and computer? You should give me a computer. So it's called foundation for a reason, because without some knowledge of chemistry, your computer will not be before you. You basically will just have you're not even having anything basically, because the monitors, the screens, all of those things are products of chemistry. So knowing it will ensure that you don't abuse your computer, and knowing it, you don't know where it would get to, but it forms the foundation of these courses. Pharmacy, you need drugs, and drugs are basically products of chemistry. So phytochemicals, that's drugs from plants, are basically what are being manufactured and processed in the whole field of pharmacy. Pharmaceuticals, we have around, pharmacists around, and if the pharmacy is not good at chemistry, you will not have a pharmacy. So we have matter, very important. Matter is the basis of chemistry, because it's matter and energy. That's the study, how they interact with one another. So it's important that we know what matter really is. And we say matter is anything. Notice that some people say chemistry is everything, but matter is anything that has mass and occupies space. So if you think of something that has mass and occupies space, be it visible or invisible, if it has mass and occupies space, it classifies as matter. So you and I, matter. Things around us matter. Even the oxygen we can't see is matter. So matter now has different phases or forms. So you can have the solid, and you can have the liquid, and you can have the gas. So you have solid, liquid, and gas, and the differences are that solids have fixed volume, fixed shape. Fixed volume, fixed shape. Then when you go to liquid, liquid has fixed volume but indefinite shape. And then when you go to gas, you have indefinite shape, indefinite volume. And notice the reason for that is that the particles in solid are together. So it gives it a shape and it gives it a volume. Then when you get to liquid, the particles become a little bit apart. It still has a fixed volume because it takes the shape of the container, but it doesn't have a shape. And then when it goes further apart into gas, you don't have shape, you don't have volume, nothing else. So, and water in its natural state is liquid at this form. But when you drop the temperature down, water takes shape because the molecules come together and it's solid. And if you want to go this way to gas, you increase the temperature. Notice that decrease in temperature, solid, increase in temperature, gas. So that is how matter, basically phases of matter. And water can exist as solid in a special condition, can exist as liquid and gas in a special condition, and then liquid is the standard condition for water, because we drink water. We don't find water as gas, of which we can purify it in that way, of which we can make it more appealing. If it's hot, we need some cold water, so we need some ice to preserve and all of those things. So that's it, and I trust that you got that part. If you didn't, it's a video, so just go back and go over it again. So then also we can also classify it in the basis of substances, that's pure and then mixture. So when something is pure, fixed composition, unique sets of properties, it can either be an element or a compound. And then when something is mixed, it means that it has more than two. Mixture, you don't mix. You can call something a mixture if it's with itself. You can't mix two bottles of water and say it's a mixture. It has to be a mixture of water and juice. And some of you understand what I mean, water and juice, because you know what juice is, water and sand or something. So you mix that, and that's called a mixture. And the mixture can be heterogeneous or homogeneous. But let's talk a little bit about pure substances. Everybody knows water because you drink water. We are made up of 70 to 75% water. If you see water, you know water because it's there. It doesn't have taste. If it has taste, you know there's a problem. It doesn't have a smell. It's transparent or translucent. I don't know what you call it. But it's colorless. That's basically what I'm trying to say. And those are the properties of water. If you add anything to it, when you start seeing color, you know that's a mixture of something. So that's pure, and that's what we call elements and compound, and we'll talk about that. We'll talk about that more in front. So I'll just quickly gloss over it just as introduction. Then when we talk about it, you'll hear it again and you'll be able to remember. And notice that for you to remember stuff, you have to repeat it over and over again. And this information are very important, and you need to pay attention to it. So you have the homogeneous and heterogeneous. We'll talk about it in front, but there are two forms of mixture. There's one mixture that you can have and then it blends in, and there's another mixture that you can have and you can still see the different individual things separate but together. So this is a schematic diagram that shows the whole thing we've just discussed from the onset. See matter at the middle, and then you ask a question: which one of them has a definite shape? Solid does, and water doesn't, or the water and gas doesn't. And which one of them has a definite volume? Water does. It takes the shape of the container. Because it doesn't have shape, it takes the shape of the volume. But for volume, you can measure the volume in the container. And then for gas, you don't have that. And another way to look at it is as a pure substance or as a mixture. And then it goes down to a solution, which is your homogeneous, and a heterogeneous mixture, and the solution or an alloy. Solution for liquid, alloys for solid. You have metal alloys. When you mix zinc and copper or any of those things, you have alloys. So it can either be a solution, liquid, or it can be an alloy, solid. That's what is a solid, alloy, liquid, solution. And then the substances can be elements or compounds. Element 1, compound more than 1. So that's it for that. So we're now going to elements. So elements are basically all around us because they are what matter are composed of. Every matter is composed of a couple of elements. So elements are matter which can be broken down into two or more pure substances, which cannot be broken down. It cannot be broken down. It's the compounds that can be broken down. but elements cannot be. So it's like the form of it. When we talk about atom, it has a similar definition, but that's what's based off. So we have 118 at the time of this presentation, or at the time of the preparation of it was 118, but now I think there's one or two more that has been added to the list. I'm not sure. There's one or two more that's been added to the list. I think some years back I heard of an element added to it. So notice that it can happen. Somebody can discover a new element and it's added to the list. So 118 elements for the sake of this slide, and then 91 are natural occurring, meaning that you find them in nature. So they are common elements, the common elements you see around, and an example is carbon, and carbon is all around us. The wood that we have around us is based off carbon. That is charcoal, carbon, it's based off carbon. And then copper, you find them in pipes, jewelries, and then the aluminium, you find them in the household utensils, the steel, and all those things. And I think it's time I can share this. So notice that in nature you have a cycle. Most times you have cycles in nature, and we as human beings, we take in oxygen and we give away carbon dioxide, and the plants take in carbon dioxide and give us back oxygen. Notice that what is moving is carbon. So we are taking carbon from ourselves and giving it to the plants, and the plants are giving us oxygen. The plant uses carbon dioxide to do photosynthesis and get food for themselves, which we later eat from the plants. So it's a very complicated system, but it's interesting if you go with the flow. So we eat the plants, we use the plants for wood and all of those things, and we beautify our lives with all of this. It almost seems as if the plants are losing. Anyhow, they get served because we just use them. But notice that when you die, you are buried in the ground and you decay, and then the plant now gets to eat you. The plant now gets to take its own share from you, and you denature, and then it uses you for nutrients. So it's kind of like the cycle of life. It's just like everything boils down to something and goes back. And even the rain, the cycle of rainfall, even the cycle of the seasons, where you have summer, winter, the rainy and the dry season, all of those things are cycles, and they're based off a system. The system runs on cycle. So that's just some fun thing I drop in when I'm talking about carbon and the rest. And notice that there are some elements that are in and out of fashion. One of them is silicon, and I'll ask you, where do you find silicon in nature? I talked about carbon. You see them in the woods and all of those things, even the charcoal when you heat stuff. So where do you find silicon in nature? Some people are wondering, where do you find silicon in nature? Yeah, you find them, you tread upon them. There's sand, because you use sand to make the glasses, you use sand to the semiconductors that we're looking at. That's $1 million industry, or $1 million worth of used in the whole thing of semiconductors. So the silicon is quite important. And then you have the lead, which is banned due to toxicity, because in very little amounts lead can be toxic, and they banned it because of some pipes that give off lead. There was a place in the US that was an issue, and it was harming the people. Medically, it was harming the people, so they had to do a whole lot of innovation. I think they've resolved that issue from the time ahead of it till now. So we have atomic symbols, and symbols are quite important because you need symbols to simplify things, to easily identify. You can't be calling the whole names, or if you're doing a reaction, you have to write carbon dioxide and plus water to give you glucose, and that's a long gist. So to make it simple, we give symbols. So elements are given symbols, which are the chemical identifiers. So usually say that one letter or two letters for an element, and sometimes it can be their Latin name. It can be derived from their Latin name, because we have 118. Just imagine for a given A, B, C, O. Sometimes you have some of them repeating. So sometimes their Latin names forms the root of the letters that have been given. Because, for example, look at copper. Copper is Cu, and you'll be wondering, where is U in copper? There's nothing like U in copper. but CO is already taken by another element called cobalt. But Cu now is for copper, so it's copanium from the Latin name. So you have mercury. Now, mercury, the symbol is Hg. And I'm wondering, why Hg? There's no H in mercury, there's no G in mercury. Where did it come from? It comes from its Latin name. So basically, you have to familiarize yourself with the elements and their symbols so that you don't make a mistake of assuming that copper is Co when it's Cu, mercury is Me when it's Hg. So that's it for symbols. And then we now have this idea of percentage abundance, that there's some familiar elements that are abundant to this degree, because if you add up all of these figures, it will give you 100 or near 100, maybe 99 point something. They give you the amount. That's the percentage abundance for them. Notice that oxygen is the highest, followed by silicon. And by the way, what I was talking previously, carbon is the plants on top, silicon is the sand or the ground underneath, and even on the periodic table, carbon is on top, silicon is under. I'll make reference to that when we talk about periodic table and electronic configuration again, so that you see the beauty of the creativity and how this thing spans out and how it makes sense if you think about it hard. But some of us, we just want to just look, we don't think about it. So that's it for this, and we just go straight into it. So we have compounds, and compounds are basically pure substances containing a combination of two or more, because it's compound. Actually, the word comes from Latin, means weight, and pounds means weight, mass, or amount. So it's more. So you have more elements come together to form compound. So you have hydrocarbons, which is a combination of hydrogen and carbon. So two of them coming together form a compound. So that's the idea. And an example of this is methane, acetylene, and naphthalene. Methane is found in your cooking gas. So all of these things are around about us, but we don't really know that they are, and they have fixed compositions, so they don't necessarily change. So you have compositions of compounds, and I'm looking for a cue, but I don't have it. Okay, it's not close by, so I don't want to go out of frame and come back, but I love to do something to illustrate this mass. Okay, I can use my hands. So compounds always contain the same elements in the same composition by mass. So take, for example, my hand has 5 fingers. So let's assume the last 2 fingers are hydrogen, and the other 3 fingers are oxygen, and all of them come together to be water. So notice that water is H2O. Then you may be wondering, why is it 11.19% hydrogen and 88.81% oxygen? Yeah, there's a reason for it, because of the mass of hydrogen and the mass of oxygen. Hydrogen, the number of electrons is 1, and its mass is lesser than oxygen. So if you had to do it on percentage, this 2, even though it's 2, they are kind of like 2 of the smallest in a sense. The pinky and then this, 2 of the small, and this are the bigger. So even though there might be such as this will be a particular percentage less, and this is a particular percentage more, so the total will be 100, but individually you have 2 and then 5, or you can call it 20 and 80 in a sense. 20 and 80, that's how you can go with it. 20 and 80, or 40 and 60 in a sense, depends on how you do the ratios, but that's how it happens. So the percentage composition is based off the masses. So that's why I said it's the percentage of water by mass. So I noticed something interesting in the properties of compounds is salt, for example, is a combination of sodium and chlorine to give you sodium chloride. We'll do naming later on, but sodium and chlorine comes together to give you sodium chloride. Notice that sodium is extremely reactive. It's an extremely reactive metal, and Chlorine is a poisonous greenish yellowish gas. You heard me. Poisonous greenish yellowish gas. And you'll be thinking to yourself, how is it poisonous and it's salt? How is that possible? But in reality, in chemistry, you have the property of an individual element can change on the basis of its interaction with something else. Your rice, when you get it from the market, it is just bland. But once you mix it up with the different spices and the tomato and all of those things, it brings out a very nice appetizing meal. But if you chew it raw, you might land in the hospital. Depends on how good your digestive system is. But in this case, it still applies where you have something poisonous but yet interacts to give you something edible. Here you go. We talked about particles and the state of the phase of matter. Remember, the solids, metal together, gas far apart, as you can see. And then when both of them interact, they interlock with themselves, and then you have crystals. These are salt crystals. There's a sodium metal. There's a chlorine gas. It's gas. Notice that it's a gas. And when you mix them up together, you have the salt, and it's a crystal, so it can easily dissolve, and you get the taste of it. So that's that. And then now we want to resolve the substance from compound to elements. Remember the example we just saw now. Sodium and chlorine come together to form sodium chloride. Then now we want to get sodium away from chlorine to go back to the individual. So that's what we're trying to do when we resolve compounds into elements. So we do that using heat. When you heat it up, you can this is seen very much when you have a mixture. When you have a mixture of salt and water, when you heat the water will evaporate and leave the salt there. And there's another technique, and by the way, I think if you stay here and the water is salty, once you keep boiling your water in a kettle or pot or whatever it is you use to boil the water, discover that there's going to be a layer formed on the metal, and that layer is basically salt formed on the layer. So you have to scrape it up once in a while. If not, it's going to do some damage to the metal over time, because you don't see it on the first go. If you keep using it, you'll see the layer, and the layer thickens over time. So you have another method called electrolysis, and I will ask you for an assignment to find out more orders aside heating and electrolysis. If you can, online, find out for your own exercise, and don't be surprised if I ask for that assignment. So I put it in the video there. For those that will watch the video, I will know if they forward an assignment. I will know if they forward an assignment or ask about the assignment. For those that don't, I'm going to be silent. So that's it. So the electrolysis, the word electrolysis, electron slicing or splitting. So basically it's by passing electric current through the compound, and this is generally in the liquid state. So once you pass electric current, notice that the word electric current is similar to the word electron. It's just basically flow of electron. So what happens is that the cathode and anode, one bit of it goes to the negative, the other bit of it goes to the positive, and that's how the separation happens in this case. And then you have mixture. So we talked about mixture previously, where we say it is a mixture of two or more substances in which the separation, in the combination of each other, you can chemically identify them. So it can be a homogeneous mixture or heterogeneous mixture. An example you have here is copper sulfate and sand. And copper sulfate is your here's it. This is what it looks like. The bluish thing is your copper sulfate, and the sand is your typical color. And when you mix the two of them together, both of them will retain their identity. They don't dissolve, they don't blend in, they just only are there. Copper sulfate is looking at sand, sand is looking at it back. and the colors are very poppy, and you see them. So in contrast to previous, where you have sodium and chlorine, and then you have sodium chloride, or you have sodium chloride in water, and then you have a solution. So that's that. So we see the image again, and then we go to the types of mixture. So the types of mixture, you have your homogeneous mixture, and the word homogeneous comes from the word home or same. People from the same family will probably stay in the same house, or should stay in the same house, and they should share the same name or the same family name. So you have that going on and on to just indicate that there's some basis of connection, or they are connected. They can blend, you blend in on the basis of one thing or the other. So the word homogeneous means same, and you see that with several words scattered around that indicates same. So it's uniform, and the composition is the same throughout. So you see the same. If you put salt and water, you mix it up, you'll see some uniformity throughout. So an example is seawater. Seawater is basically salt water. So it's salt in water. That's seawater is salty water. So it's also known as a solution, because you have solute plus solvent to give you solution. We'll see that ahead. And then you have the heterogeneous, which is non-uniform, meaning that it's not uniform. So it composes, it's the composition varies throughout. An example of that is the rock. It's a rock because it's a mixture of different kinds of rock. There's igneous, metamorpho, it can be mica, quartz, and feldspar. We'll see that here, and yeah, it's just here. So notice that this is homogeneous because you have copper and zinc, and these two metals, when you heat them, you can blend them together, and then you can have a uniform mix. You can't even tell there are two different metals that mix. And I think this is either bronze or brass. One of them. It looks like gold, but it's not gold. This is the fake gold that can be sold. This can be particles of, but gold is gold. So that's it for homogeneous. And then you have, and remember, we call this an alloy. Call this an alloy because it's a mix. And then you have the granite, and the granite basically is a mixture of feldspar, mica, and quartz. So you can see the individual; they're looking very different. It's not consistent, it's non-uniform. This is uniform, this is non-uniform. So basically that's the two kinds of mixture, your homogeneous and your heterogeneous. So I think this is where we'll end the video in solutions. So we'll continue in the next part, but just to give us what the solutions are. Solutions are basically a combination of your solute and your solvent solution. So solvent are basically the liquid, they're commonly liquid, and water is classified as a universal solvent. So, and they are the ones present in larger amounts. And this is what you experience with a homogeneous mixture. And then the solute is liquid, can be solid, it can be gas as well. So a typical example is water is a solvent, salt is a solute. You mix them together, you have seawater. That's the example that we have. So that is it for the first part, and I hope it's fun. It's not too boring, at least the sound that's playing in the background and how it is you're flowing with the slides. So please try as much as possible to watch it more than once. Do it once, watch it again. The parts where I'll ask more questions are in the future slides and the future presentations or videos. So you just follow through, and this is the first part. We'll have homeworks, we'll have quizzes, we'll have some activities to engage us. So for the fact that you're watching it online, because some of the students that didn't make it to the class will also watch it as well, but we'll see ourselves as the week progresses. So every week we have our classes, be it online, be it physical, we'll have our classes. So I'll try to make the video in this format and be dropping it and ensure you watch them, because I will know whether you're watching it or you're not watching it. So that's it for this. Hope to see you on the next one. So take care. Bye for now.